All right, welcome back, you little chemistry hoodlums. We are going to try to clarify, hopefully clarify some of the stuff you guys were working on in class around atomic structure. How can you tell how many protons, neutrons, electrons you have, right? So we're going to tidy up a little bit about mixtures and stuff first, though, all right? So mixtures versus pure substances. I know we've kind of hit this subject pretty hard the last couple of days. Just a little bit more distinction I want to do. All right. So one of the things we did in the lab was we created a mixture, right? And then we separated that mixture. So one of the things I want you to remember that distinguishes a mixture from, say, a compound is mixtures can be separated using physical processes. Now, pure substances can't be. And when I say a physical process, I mean anything I'm doing that's not causing a chemical reaction. So I'm not breaking bonds or forming new bonds. All right. So what we did in the lab yesterday, we added water to our mixture. In that case, sometimes adding water does cause a chemical reaction, by the way. But in this particular case, the adding water didn't cause any bonds to be broken or any new bonds to form. All right. So adding water to dissolve the salt was a physical process, not a chemical. All right. And then what you guys are doing now is you're waiting for that water to evaporate, right? That is, again, the evaporation of that water is a chemical process, it is a physical process, not a chemical process. So mixtures, we can separate those using physical processes, whereas pure substances cannot. All right. Now, we're going to do one step down. So our two pure substances we talked about, they're either elements, pure elements, or they are compounds. All right? Now, compounds we can actually separate using a chemical process. So, for example, if I had some water in a beaker or something like that, if I run electricity through that water, right, if there's a little electrolyte present, what I can do is I can take that water, which is H2O, and split it up into oxygen and hydrogen. Okay? So in that case, I am actually separating that water into its constituent elements. But in order to do that, I had to break the bonds, which means I did a chemical reaction, not a physical process. Okay? And last but not least here, we have elements. Okay? So elements, again, those are the things we find on our periodic table, and they're our simplest form of matter. So if I have just gold, for example, all right? There's nothing chemically I can do to gold to make it into something simpler, right? If I were to split gold into its individual atoms, I would still have gold atoms. I wouldn't have atoms of something else, all right? So the only way to change gold is to actually get all the way into its nucleus and cause some change there. And that is not something we can ordinarily do. We need really special circumstances. And that requires nuclear reactions, all right? So, and that's actually a later chapter. We have our next chapter, in fact, will be devoted to nuclear reactions. We kind of have our own little unit on nuclear chemistry. And then chemical reactions and processes is the bulk of our year. We'll spend a lot of time on chemical processes, and we'll also learn about nuclear processes a little later. But I just want you to make that distinction. Mixtures, probably the easiest thing to separate. We can do that with things like filters or evaporation, okay, or just mechanically separating. Compounds, we have to resort to some sort of chemical reaction to break them down. And elements, we can't really break down using ordinary means. We have to get into that nucleus somehow, which you and I, with our normal technology, we just can't do that kind of thing, okay? Plus, it's dangerous. All right. And the other thing, another important bit, just a guiding principle, and this is going to be important to us with all of our chemical reaction stuff, is just making sure we understand this law of conservation of matter or law of conservation of mass, right? So all physical and chemical processes, matter is conserved, all right? And so what that means is the total mass of materials before and after a physical or chemical reaction is exactly equal. All right. So let's say I burn a match, right? So if I light that match, I let it sit there and burn, right? And what we're left with is just some charcoaly ash stuff, right? And the mass, if I were to put that match on the balance, right, next to it before and after, the match would have a smaller mass. Now, does that mean that I have lost mass or destroyed mass? No, it just means some of the mass escaped, all right? And that's because the majority of the mass of that match, as it combusted, became either water vapor or carbon dioxide, which are gases, so they just escaped out into nature. All right, got interrupted there for a second, so I lost where exactly I left off. But the idea with this is if I could capture all that CO2 that was burned off and all the water vapor and the ashes and charcoaly stuff I'm left with and put it on a balance, I should, of course, end up with the same total mass. All right? So mass before equals mass after is that's simply put. So if I have 12 grams of carbon and I react that with 32 grams of oxygen, I should get 32 plus 12, 44 grams of CO2. All right? And it's that easy for now. All right. Now, atomic structure. So this is what you guys started puzzling your way through today in class with Chem Quest number 6. All right? So I wanted you guys to try to look at those models of an atom and try to piece this together so you guys have a little more context with which to move forward. Okay? So, first of all, atoms, and I hope you guys have at least some background info here to work with, but atoms are our smallest representative particle of the elements. And when I say representative particle, I mean that's the smallest particle you can get and still call it that something. So if I have a helium atom, so if I were to break that down, I get down to an atom of helium, and if I went any smaller than that atom, it's no longer helium. Okay? And so that's the way I think of it. They're the smallest representative particle, but of course we got the protons, neutrons, electrons in that atom, and those are made up of even smaller things, and then things get all crazy weird on us when you get that small. But atoms are the smallest representative particles. All right? And the three primary particles that we're going to focus on in our atoms are protons, neutrons, and electrons. And again, I hope you've at least heard these terms and you have some understanding. All right? Protons have a positive charge and a mass of about 1 AMU. Neutrons have 0 charge and about the same mass as the proton. And electrons have a negative 1 charge. And they do have some mass, but it's so insignificant that with most of our calculations, they're not really going to be important in terms of mass. But that charge is important. All right? So, our protons. All right. So, protons, they're a positively charged particle and have a mass of 1 AMU. All right? Now, we're going to use this kind of, it's not really a measured unit, an atomic mass unit. It's kind of it's a relative unit. So, 1 AMU, just FYI, is defined as 1/12 the mass of a carbon-12 atom. All right? Now, we can't actually measure, put an atom on a balance or 1 proton on a balance and measure it to 1 AMU. It's actually a relative scale like this compared to that. All right? But it works out really well for us when we get into moles and stuff. But it's a very well thought out, determined value, but it's not a direct measurement. So I just want to throw that out to you guys. All right? So what you have to understand about protons, right, is they contribute +1 charge per proton and +1 AMU to an atom. All right? And protons are what give an atom its identity. All right? So the number of electrons in an atom and the number of neutrons in an atom is variable. And certain conditions can cause those numbers to change. But if we're going to call something carbon, we know that it has 6 protons. It might have 7 or 8 neutrons, and it might be ionized to gain or lose electrons, but all carbon is going to have 6 protons. And if it doesn't have 6 protons, it is not carbon. So likewise with oxygen. All oxygen atoms have 8 protons, right? If it doesn't have 8 protons in the nucleus, it is not an oxygen atom. It's an atom of something else. So that's what I mean when I say protons are what give an atom its identity. All right? And it is indicated by the atomic number on your periodic table. So if I look at oxygen on the periodic table I gave you, you get this little box, the big O in the middle, and it's going to have an 8 above it and a 16.00 below it. That 8 is the atomic number, and it's also the number of protons. Okay? That's what the atomic number tells you. And when we talk about the location of protons, so protons are in the nucleus, right? And you guys saw that in the models in the Chem Quest today. Neutrons are a neutral particle. That means they have zero charge, right? But they have a mass about the same as a proton. So, zero charge and plus 1 AMU, just like a proton. Now, they only contribute to an atom's mass. They don't really do anything in terms of charge, and that's because they are neutral. So they add a little extra mass per proton or per neutron to the nucleus, but they don't add to the positive or negative charge of that atom. All right? Now, the number of neutrons is not, so like protons, like I said, if I have carbon, all carbon has 6 protons. Now, may have 6 neutrons, or 7 neutrons, or 8 neutrons, depending on what variety of carbon we have. Okay? So the number of neutrons for a particular type of atom can vary, whereas the number of protons is a constant. All right? So, if I look at like carbon-12, for example. Now, carbon-12 is referring to the fact that this particular carbon atom has a mass of 12. So, we know because it's carbon, there are 6 protons. And there's 6 protons because it's carbon. All right? Now, the overall mass I know is 12, right? And so that means it also has 6 neutrons. All right? So, how do I find how many neutrons I have? I take the mass number minus the number of the atomic number, the number of protons. So 12 is my mass, 6 is my protons, that leaves me with 6 neutrons. Now, if I have carbon-13, which is also carbon, and of course has 6 protons because it is carbon, right? I can then take my mass number, which is 13, subtract my protons, and that tells me that I have 7 neutrons in that variety of carbon. That was an obnoxious bell. All right? And of course, our neutrons, as you saw in your models today on the Chem Quest, are also in the nucleus. All right? So then we need to define this term isotope. All right? So when we're talking about isotopes, we're talking about the same element, right? Which means they have the same number of protons, right? Because that's what gives the element its identity. All right? So they're going to have the same atomic number, but they have a different atomic mass. So if the number of protons for an element cannot change, the mass can change only if we have a different number of neutrons. So going back to our carbon example, carbon 12, 13, and 14, that's referring to the mass, the 12, 13, and 14. All carbon has 6 protons. If it didn't have 6 protons, it would be a different element. All right? Carbon 12 has 6 neutrons. Carbon 13 has 7. Carbon 14 has 8 neutrons. All right? So we call those isotopes of carbon because they are the same element, but they have a different atomic mass. And some isotopes end up being radioactive, but we'll talk more about that in chapter 28 next. All right? Now, how is an atom different from an ion? So when we call something an atom, you got to pay close attention to language, right? If we're calling something an atom, we are saying that it's neutral. All right? And that means the number of protons is equal to, that should say electrons. Horrible, horrible science teacher, right? When we say an atom is chemically neutral, that means the protons number is equal to the number of electrons in that particular atom, all right? Now, ions, on the other hand, are not neutral, okay? They could have either a negative or a positive, okay? So, in order for an atom to become an ion, that means that we have to change how many electrons there are because we can't change the number of protons. What happens if I try to change the number of protons? All right, and so in order for me to have a negative or positive charge, that means I have to have an unequal number of protons and electrons. All right, so let's say I take a fluorine ion, right? So let's say it's fluorine, which is going to have 9 protons.
God, today's our thing for...
Grady just interrupted me. Dang it. All right. So fluorine has 9 protons, because if it doesn't have 9 protons, it's not fluorine, right? So now, if fluorine is to be neutral, it would also need to have 9 electrons. All right, because a +9 and a -9 equals 0, right? Now, let's say I have 9 protons, so it's still fluorine, but let's say we get an extra electron in there. Okay, so a +9 and a -10 comes out to a -1. And so we would say that fluorine ion has a charge of -1. And that charge happens because the number of protons is not equal to the number of electrons. Okay, so electrons are a negative particle, and we say they have pretty much 0 mass. Again, they do have some mass, it's just insignificant for the most part. All right. Now, electrons do have a pretty beefy charge for their size. They have a charge that's equal and opposite to that of a proton, right? So it attributes a -1 charge, but pretty much no mass. All right. Now, that chemical behavior piece, that's later. We won't worry about that right now. All right. So the number of electrons in an atom is equal to the number of protons. All right. And the reason we say that's equal is because we're calling it an atom. And if we call it an atom, we know it's neutral. And if it's neutral, our plus and minus have to be equal in number. All right? Now, the number of electrons in an ion is not equal to the number of electrons. It's equal to the atomic number, or the number of protons, minus the overall charge. So let's say I have an ion with a charge of -2, right? Like oxygen would normally have. All right? So how do I know how many electrons are in an oxygen atom? So I have O2 minus. So that's telling me that my oxygen ion has a -2 charge. All right. Why they write 2 minus instead of -2? That's just normal chemistry. This is what they do. All right. So to find my number of electrons, I'm going to go my atomic number minus my charge. All right. 8 minus a -2 is 10. So I would know that an oxygen, well, that should say ion. Good golly, 2 mistakes, right? The oxygen ion, the charge of -2, would have 10 electrons, because I'm going to take my number of protons in oxygen, which is 8, and it's always 8 for oxygen, minus the -2, which is my charge, gives me 10. So 10 electrons in that ion. If there's an oxygen atom, it would have 8 electrons, so that I end up with 0 charge. All right? I'm getting a little long-winded. I'm sorry about that. But quick thing on symbols and notation. On your periodic table, right? So, sometimes we see, let's say something written like this. So let's go back to oxygen. All right? So oxygen, actual atoms of oxygen are ions. They're not going to have a decimal mass. So if I look at, like, let's use nitrogen. Nitrogen. You see the number 14.01 and the number 7 next to nitrogen. There's like a little 3.0 down there with the name, right? All right. Now, that's the atomic number. The average atomic mass, that's electronegativity, which we'll worry about later. And then, of course, is the name. All right. So one way we might write the symbol for various isotopes of nitrogen is we might write a 14 and a 7. Now, the 14 doesn't have that 0.01 attached to it, because the 14.01 is the average of the isotopes of nitrogen. All right. This particular nitrogen isotope has a mass of 14 exactly. All right. Now, sometimes we might see a little symbol up there to the right. So that top number on the left is my mass. The bottom number is my atomic number. This is mass number, and that's my charge. All right, and then from that, I can get how many protons I have, which would be 7, because that's our atomic number. My number of neutrons would be 14 minus 7, 7. And my number of electrons would be 7 minus a -3, 10. All right? And that's how I would solve for those things. All right? So protons is equal to your atomic number. Neutrons is equal to your mass number minus your atomic number. Electrons is equal to your atomic number minus your overall charge. All right? And that's how we do that. Of course, you guys will need to memorize that and practice it. Talk to you later.